Okay, I think we can start. Yeah, so it's a great pleasure to have Ilai Guendelman with us today from Princeton University. Ilai is a bachelor in Be'er Sheva and Ben-Gurion University, then a master and PhD at Weizmann Institute, studying large-scale circulation in exoplanets, and now is, for the last year or so, is at Princeton University as a postdoc. And he shifted back to Earth, looking on warming response in global storm resolving models. Eli, please take it away.
Yeah. So thank you for having me, and yeah, I'm going to talk about some of my postdoc work, and this is my work in Princeton, and it's with collaboration with people from GFDL, and it's about a warming response in a global storm resolving model, and I'm going to start with an introduction, and it's very basic, and I assume most of you already know that, but I think it's a good layout for the talk. So just a little bit about general circulation model, and all the models that I'm going to talk about here now are mostly global models and not regional models. So when we are talking about the general circulation model, we are talking about a numerical solution for coupled differential equations that can generally be described as this, where x is a state vector, with whether it's mass, momentum, energy, or any other trace that is relevant that we want to know about it. And we have those terms in the right-hand side that we can describe as the dynamics. R can be described as the resolved dynamics, so everything within the grid cell or larger. U is the under-resolved or unresolved dynamics, so everything that is subgrid. P are all the processes that are contributing to the thermodynamics, so everything that diabatic heating, microphysics, surface interaction, everything that you can think about that can enter into P, so it's that. And F are external forcing. So when we are talking about general circulation models, usually the most problematic things, or the things that we are uncertain about and result in biases in the models, are the unresolved dynamics and the physical processes. And basically those two terms are what we usually call the physics of the model. And the resolved dynamics are the dynamical core, but of course the physics at the end will affect the resolved dynamics. And another thing, and this is basically what we want to explore, are the external forcings, which are different anthropogenic forcings, solar forcing, historical forcings, and basically the question that we want to ask is how the climate responds to this type of forcing. Now, if we'd had a perfect model, we wanted to have a pretty good resolution, meaning that we want to minimize the unresolved part. Still having an unresolved part in the physical, we need a good representation of that. But given that it's a perfect model, we need it to be easy and cheap to explore different forcings and to run it for climate time scales, which are an order of 100 years. Now, when we look at traditional models, we usually talk about models with a resolution of an order of 100 kilometers. So it's not that great of a resolution if you want to resolve small scale phenomena. We know that our representation for the physics is not perfect. Model of biases, and the spread of the model when we explore different forcing is large. But on the other hand, most of the models are relatively easy and cheap, and I think that the best example for that, or the best evidence for that, is just the amount of intercomparison projects that use a lot of models. So we are able to run those types of models for a lot of time and a lot of different experiments. And in this talk, I'm going to talk about a specific model that's going to focus on what happens when we increase the resolution. And this is what we are calling a global storm resolving or cloud resolving model. This picture that I'm showing you here is an OLR picture from 10 different action model, and one of them is also from observations. Not action model, diamond model. So the diamond models are an intercomparison of GSRMs, and GSRMs are usually, when we are talking about GSRMs, are a kilometer scale global models. All of them are less than 10 kilometer resolution. Most of them are less than 5 kilometer, and they are solving on it. They're using a non-isostatic dynamical core. Now, just for context, we know that weather prediction models usually run on a resolution of 13 kilometers, so these models have a finer resolution than those that we use for weather prediction. If you take the traditional GCM, it's 100 kilometers, so we have at least 20 times finer, or the GSMs are 20 times coarser than GSRMs. And the reason that we are going to that kilometer scale is because in that kilometer scale, deep convection is mostly resolved. And just few words about the diamond runs. So the diamond runs are an intercomparison of GSRMs, but they are basically limited in the time. So it's only 40 days period of control climate. So we have 2 periods, one around summer, one around winter. All the models, another limitation is the fact that we are using only atmospheric only models and not a coupled model, so it's forced by prescribed SST. And this is just a representation of that month compared to observations. We can see that it looks similar to observation. This is the precipitation, but we still have a spread within the models that we are looking at. Now, so what GSRMs are doing better or worse or the same compared to traditional models? And this is just a scatter plot of different cloud properties and how GSRM looks. So the black colors are different GSMs, like traditional ones. The brown ones are the different GSRMs, and the cyan triangle is just an estimate of observations of different cloud properties. So here we are looking at upwelling long wave TOA, so OLR, and this is precipitable water. And when you look at this phase space, we can see that GSRMs do a better job in representing the observation. However, if we look at the phase space of albedo and cloud fraction, you can see that basically the GSRMs are all over the place, similar to the GSMs, GCMs, and there's basically no improvement. One could speculate and say, okay, this is maybe more controlled by deep convection, and this is the reason why GSRMs do better job. Here, shallow convection is still important for the cloud fraction and the albedo, so it makes sense that GSRMs won't do that much a better job than GCMs. Yeah. Another part where GSRM seem to do a better job is when you look at the precipitation distribution. And basically, when we are looking at the precipitation distribution, here are like different ways to look at it. So in the left-hand side, we are seeing the frequency distribution of each precipitation rate, and this is the amount of rain that contributes of each precipitation rate. So if we look at the frequency distribution, we can see that, and yeah, I didn't say it, but the top are the diamond models, the middle ones are the high resolution CMIP6 models, and the bottom ones are the AMIP models, and the blue and red colors are different observation estimates. The reason that they look different between here and here is because we are looking at two different periods. Here is just 1 month, and here is a climatology of few years around the same month, so all are around August. And when we look at the frequency distribution, it actually looks that we are not doing that much better using GSRMs. We still have too much drizzle in GSRMs. But if we focus on high precipitation values, we can see that the tail of the distribution seems to agree more than if we look at the high resolution or AMIP models. And this actually translates to the amount distribution, where the amount distribution in GSRMs look more or less better than what we look at the high resolution models and the AMIP runs. So the take point from this slide is that GSRMs have some improvement when you are looking on extreme precipitation, maybe extreme precipitation, maybe it's moderate to extreme precipitation values, or better representation of the distribution of precipitation. So we know that they are doing better. So what we are going to look at now are runs of XShield, which is the GSRM that I'm going to focus on. So this is an AMIP run. Again, we are looking on a situation where we forced by SST for the years 2020 and 2021. And again, if you just compare it to a normal diamond protocol, we are way longer than the normal diamond protocol. On the other hand, if we are going to a normal climate model, it's still just 2 years compared to 40 or 50 years that we're usually looking at. We did 3 different perturbation simulations. So plus 4K, and this is the one that I'm going to talk about in this talk. A fixed SST with 4 times CO2 concentration, and the combination of the two. We are also working now on doing a patterned warming simulation. And the most important thing is that we don't have deep convection or gravity wave drag parameterizations, but the shallow convection is still in place. And in some of the parts, I'm going to compare XShield result to CMIP6 AMIP runs. Some of them I'm going to look just at the results from the XShield simulations. So if I'm just going back to like the judging the XShield run compared to the way that I judge the GCM run, the normal GCMs, so we've improved our resolution. So we are resolving now more small scale. We are still not perfect, because in order to go perfect, you need to go to a molecular level resolution. It's very difficult. So, but we are fine. But as I already showed you, even though we have better resolution, the models still have some biases, although we have some improvements. But the most difficult thing with this type of model that is not easy and cheap to run, just for having an order of magnitude, in order to run 1 year of AMIP, it means that you need to use 7 million CPU hours, which if I'm doing it, if I'm comparing it to running a fully coupled model in a relatively high resolution, so I'm talking about 50 kilometers, I just looked around. So with the same CPU time, you can run 400 years of a fully coupled model, air system model, and yeah. So just, it's a lot of computer power just to run 1 year of this type of simulation. So as I said, this is a limited run. Another limitation of this type of model is that the output is usually very heavy. So it's not all the output is saved in the native resolution. So there's some type of a coarsening process that goes out. And sometimes after the fact, you realize that you...
What?
Is there a question or? Yeah. So after the fact, you probably realize that you need some type of the variables in the native resolution that you don't have. So this is just a caveat that has these models. And given those type of limitations, I'm going to focus on 3 ways that we evaluate or we analyze the data. So one of them is just a qualitative comparison to CMIP6 models. Another way is doing a more quantitative comparison to CMIP6 model. And the third thing is, well, we have a fine resolution model, so maybe we can look at response to warming on the grid cell size and see if we can see something that is interesting and worthwhile to look at. So the first thing that we are looking at are the relative humidity and temperature changes. I think it makes sense to look at relative humidity and temperature because relative humidity and temperature are things that are influenced by large-scale circulation, but we have the reasons to believe that they will be influenced also by small-scale or deep convection things. And we might think that if we resolve better deep convection, the response to warming will be a bit different than coarse GCM that doesn't resolve that. But when we are looking at this is the 2-year mean X-shield runs. This is the AMIP multi-model mean, which is just about 11 models, so it's not a lot of models. But basically, what we can see is if we look at the vertical changes around the tropics, which are mostly relevant when we think about deep convection, the changes are very similar, like just by eye. We don't have a lot of differences between X-shield response and CMIP6 response. The same thing we can say about the relative humidity, where there are, within the troposphere, the changes are very mild and basically almost zero if you take some type of mean, especially when we consider changes in Clausius-Clapeyron, that we know it's 7% per Kelvin, and here are the changes are again in percent per Kelvin for the relative humidity. Another thing that is interesting is even the spatial shape of the changes is similar to the changes that we can see in the CMIP6 models. Now, given that X-shield and CMIP6 models predict similar changes on relative humidity, and we know that the amount of, I just want to say, I'm going to focus a lot of precipitation, but these are related things to precipitation. So we know that the changes in relative humidity are mostly almost no change. We have almost no changes in relative humidity within the troposphere, but we know that the amount of water vapor increases by 7%. On the other hand, we know that the global mean precipitation is constrained by energy balance, and it will increase by 3 to 4% for isolated warming. Again, this number, if you take the full global warming effect, where we also consider the radiative effect of CO2, it's 2 to 3%. And when we are looking at the annual mean changes of CMIP6 model, and this is the numbers that you see in the parentheses are basically the spread within the year. So 95% of the yearly changes within the different models in CMIP6 years are between these two values. You can see that, first of all, actually is in the lower end of the changes, but it's more or less within the range. So we know that these changes are important, are 3 to 4%, but the difference between this number and this number just means that we'll have circulation changes. And when we're talking about circulation changes, the first thing that we are looking at are the large-scale circulation, and we can talk about the Hadley cell. Here I'm just showing you the mean meridional stream function on 2 years of X shield and CMIP6 models and mean models, and yeah, we can talk about the widening of the cell. And when we are looking at, for example, here, the black lines are for the width of the control simulation. The red lines are the width of the plus 4K simulation. We can see that we have similar response. If we look at the response, we can clearly see that we have weakening of the circulation. So red over dashed line is weakening. We have also a deepening of the circulation and a widening of the circulation. And what's interesting is, again, if we look qualitatively at the response, we can see this is very noisy simply because it's only 1 ear, but the pattern of the changes are very similar, saying that having this high resolution model doesn't result in a different change. So the large scale is mainly what controls the response of changes of the large scale circulation, which makes sense. It's not that surprising. Now, if we want to do a more quantitative analysis, so let's say we want to look at the cell width changes in compared to CMIP6 models and the cell strength changes, we can start and do something like that. And what we are doing here, we are saying, okay, we can look at how the climatology changes within the model. So this is percent changes. And we can say, okay, in some cases, most cases, the changes, if we look at the width, are within. Maybe here it's a bit outside the spread, but if we're looking at the climatology and this is only 1 year run, it's not a fair comparison. So the better comparison would be, let's look at the spread of a year-to-year basis. So I'm looking at each individual year and looking at the change of each individual year. And here comes the part that we are using an AMIP model. And because we are using an AMIP model, it's okay to do an year-by-year comparison because basically we are using the same SST for each year, but just applying some type of a perturbation to it. Now we have 2 years, so we can reduce a bit our uncertainty and look how those changes look like by doing a 2-year rolling mean on the AMIP runs, and then we have only 1 dot for the X-shield run. And in most cases, X-shield response is inside the inner quartile range, but in some of the, like if you look at the southern hemisphere width changes, it seems that it's still within the spread, maybe in the lower widening range. But again, the big picture is saying that that Hadley cell changes in X-shield are within the range of CMIP6 models. Now we can do a similar thing for the zonal mean, zonal winds. Again, qualitatively, they look similar, like a similar change. We have strengthening of the jet, we have forward shift of the eddy-driven jet, but what I want to say here, so I'm doing the same analysis here, and I'm looking, and basically I'm seeing that it's again within the range, but here we can use the fact that, and I'm looking, and I will focus mostly on the southern hemisphere because I know that for the southern hemisphere I have a dependence of the change with respect to the control position for the climatology, what we call some type of emergent constraint, and we can generalize it a little bit. And if I'm just looking at the bottom panels, we can see that the changes, if I'm looking at the strength here, it might look that the change is outside the inner quantile range, but if I'm looking at the fact that the change in response to warming depends on my position, the agreement of X shield with CMIP becomes even better when I'm taking into account this fact. And it's true also when I'm looking at this thing. So what I want to say here is basically that in some cases we need to take into account the fact. So just looking at the spread this way is not necessarily the best way to look at the spread, and maybe in some cases we would need to take into account the fact that the changes might depend on the base state of our simulation, and then maybe we'll decrease the discrepancy or maybe increase the discrepancy. Okay. So we've looked and we've seen that the circulation changes are more or less similar within X-Shield and CMIP6 models. So the next question that I'm going to ask is how the precipitation distribution changes, and more specifically, does X-Shield response differ significantly of the distribution now differs, which I want to remind you, we assume that that GSRMs do slightly better when we consider the distribution of precipitation. So this is why we want to ask this specific question. And the reason why we are going to a distribution is because basically to avoid looking at a map, we are aggregating statistics, and that way our result is can become more significant in statistical terms. And what I'm showing you here is some type of a cumulative distribution function of percentiles. This is like the y-axis. The x-axis is the precipitation value, so millimeters per day. The solid black line and is X-Shield in its native resolution, and the blue line is IMERG, which is type of a estimate for observations. And we can see that first of all, like we've seen before, X-Shield has too much drizzle, but when we are looking at everything between 10 and 100, when we are looking at the native resolution, it looks like IMERG and X-Shield have a very similar distribution. When we coarsen X-Shield response, X-Shield distribution, it starts to look like more like a CMIP6 model. We are going to work on with a coarsen output, but I'm not showing you this here now, but the response to warming is very similar if I'm considering the native and coarse resolution, so it's fine in that term. Yeah, so this type of figure is going to appear in the next 2 or 3 slides, so it's important that I'll explain it well. So the x-axis is, instead of talking about the percentile response, I'm talking about the value of the control percentile. So instead of talking about, for example, the 99th percentile response, which are the black the different circles, I'm talking about what happened in the control, what happens to the precipitation response in the control climate, that in the control climate were 100 millimeters per day. So if I'm looking at X-Shield, for example, I'm seeing something of about 5% per Kelvin increase, meaning that in the plus 4K warming, everything that was 100 millimeters per day is now 120 millimeters per day or something like that. Yeah, so basically if I'm just describing the response of X-Shield, most percentiles show an increase in precipitation. The higher percentiles show more increase than the lower percentiles. And at large, X shield is within the range. Okay, so the black solid line is the multi-model mean of CMIP models. The shading is, again, I'm talking about a standard deviation of, when I'm considering the standard deviation, is I'm considering the response of each individual ear within CMIP6 models, within all those models. So this is the spread that I'm looking at. And when I'm looking at the spread, I'm seeing that at most percentiles, and in fact, at most percentiles that we really care about that, so everything that is larger than 1 millimeter per day, actually is within the range. In lower percentiles or in lower precipitation rates, it's outside the range, which might be still interesting. And another point that is interesting is that the response of the extremes is in the lower end of the different CMIP6 models. Now, because these parts look interesting, we can separate and look at the ocean response and the land response separately. And we can see that we have a similar response in the ocean to the global response, which makes sense because most of the planet is ocean and the precipitation is much more stronger over ocean than over land. But when we look at the land response, what first popped in the eye is that the discrepancy between X shield and CMIP6 models become larger when it starts to become significant even for percentiles that we care about. So things that are larger than 1 millimeter a day. So it's interesting to look at the land, where specifically in the land it becomes relevant. And we can look and differentiate between tropical response and mid-latitude land response. And when I'm talking about the mid-latitude land, I'm talking only on the northern hemisphere. And the precipitation over the mid-latitude, and so just describing the response, we can see that the response on X shield is similar for the mid-latitude and tropical land, where high values increase, low values decrease. The same happens on tropical land. But if we're looking at the comparison between X shield and CMIP6 models, it's interesting to see that the tropical land, where actually deep convection is mostly important, is more or less, you can basically indistinguish X shield between different CMIP6 models, maybe just a little bit on the extreme, when you look at the extremes. But when you're looking at the mid-latitude response, the response of the mid-latitude is significantly different. And now we are talking about any values that are lower than 20 millimeters per day. So pretty significant precipitation events within CMIP6 that are different, that have a different response compared to the CMIP6 response. Interestingly enough, is that when we look at the extreme response, which this is, again, the circles represent the 99.9 percentile, the response of X shield and CMIP6, at least 1 year of X shield and CMIP6 response of the mid-latitude agree within almost all models, agree about the response, where for the tropics response of the extreme events, the spread is pretty large. But this is just a different point. What we are interested in is the fact that we have a very large difference between X shield and CMIP6, and we can ask, okay, maybe it's just during summer where precipitation over mid-latitude land is mostly convectively driven, but we can see that first of all, one winter that behaves very differently from all of them, but still, even the second winter, the precipitation of the lower percentiles are still or at the edge of the spread that we defined, or very close to the edge or outside the edge, and basically for all seasons, the deviation is significant. So it's not a seasonal thing. Interestingly enough, if we look at the annual mean response, not only of the precipitation, but other surface fluxes, we can see, and again, this is the mean, and these are the spread within the years, responses within the years. We can see that the surface fluxes are outside the range for both the latent heat response and the sensible heat flux. And this is just an indication that this is a response of the surface atmosphere interaction. So in this part, you can say, okay, maybe it's just the fact that maybe X-Shield uses some type of a land model, but I think that the more reasonable way to think about that is to say, okay, we have a fine resolution model. It means that we resolve better interaction between atmosphere and land, which result in a different response of the precipitation response. Okay, so the last thing that I want to talk about, which is now not necessarily talking, and it's just at this stage, it's just some type of a statement. We don't really have an understanding of what's happening, but I think this is an example of what we can use these types of model in order to better understand the small scale dynamics. So what I'm looking at here are just composites of different precipitation extreme events over different latitudes and the response to warming. So the contours are just the extremes, the colors are the response to warming in percent per Kelvin, and this is over the tropics, this is over the mid-latitudes, and we can see that the response, and when I'm looking at the composites, so we are talking about grid points, but basically the scale that we are looking at is each grid point is 3.25 kilometer. So basically it's a 200 by 200 kilometer box. So something that is about 2 grid cells of a normal GCM. So basically what we are looking at is the response to warming within a grid cell of a GCM of precipitation extremes. We can look at it, it has a structure. It's more obvious over the mid-latitudes. It has also a structure on over land. And we can see that basically what we are saying is that it's not necessarily that the strongest increase will be at the peak of the precipitation, but rather in the there is some type of an organization response within the grid cell size, and it becomes even clearer when we are looking at the mid-latitudes, where the peak of the precipitation is the point that increases relatively the least compared to its surroundings. So maybe we have an expansion or each extreme event becomes larger or becomes more intensified. And we can see it also if we are looking just at, so I can do and ask how much do I relatively increase if I'm looking just at the middle grid point, and now I can go outside one grid point in average and go up to the 32 and look at the average increase of that entire grid point. And we can see for the tropical case, it's more or less constant around at 8% per Kelvin or so. We have some type of a non-monotonic response, but it's more or less constant, especially when we are talking about the response of the extratropical or the mid-latitude extreme, which the relative response increases the more I am taking a larger mean of that. Now, another interesting thing is if I'm looking at a different season, it has a very different response, which again makes sense if we're going back to what type of the precipitation extremes, when I'm talking here only about the mid-latitude extremes. And yeah, so basically it's the same, and the DJF has a very different response from the JJA. And I think that the main point of that is saying this is another pathway to use these types of model, because this is, I think, one of the most obvious. Now, the only issue is how you further analyze depending on the output that you have, which brings me back to the problem that not always you have the output that you want, because it's a very heavy output out of this model. Yeah, so I'll just finish with some conclusions. And again, GSRMs are a new tool, relatively new tool, especially when we consider it as a tool for studying the response to warming, but not only that. The main issue with GSRMs is they're still limited computationally. So in the near future, there's not going to be a climate scale run of GSRM. I don't believe it's going to be. So the idea is that we need to use these types of model and to try to utilize them in a smart way. And we need to think of how to utilize them and how to compare them in a meaningful statistical way with the traditional models. And I hope that I showed some cases where we can do that even quantitatively. And the main result that came out of that is that the response to warming, when you're looking at the large scale, it's actually very similar to the traditional model. So maybe in that case, it won't be the most obvious use for those types of model. And maybe just looking at small scale and short scales phenomena to understand how they change within the climate, and just to have better understanding of the physics of the changes of the small scale phenomena, maybe this is the better use for this type of model. And yeah, I'll finish here and take any questions if there are.
Great, thank you very much. Fascinating talk. Do we have questions? I can start. I have one. So, do you have any speculation of what causing the different response, especially in precipitation in mid-latitudes? Why do you get such an increase in extreme precipitation outside?
Are you talking about this thing?
Yeah.
No, I still don't have any speculation for that. I think I'm not aware. I don't have a very good idea of why is that actually.
You know if anyone is looking on the convective aggregation mechanisms in these types of models, if I don't know, using the moist static energy budget or other tools to better understand there and the response of it.
Yeah, we started to look a little bit. The problem again goes to when we started to look at, when we thought about looking at convective aggregation and things like that, but the problem is that we stopped doing that simply because we don't have the variables in the native resolution, and we thought it would be important having the them in the native resolution, but maybe it's still worth looking at, even if we're looking just at the 25-kilometer output. But yeah, it's probably something that we will do, but we focused mostly at just the precipitation, and it's mostly like a very descriptive way, simply because basically almost the only variable that we have in the native resolution is the precipitation. So so this is why we focus on that. But yeah, sure, it's something that we are thinking about, and I'm guessing other people are thinking about looking at that. But again, it depends what you want to look, and yeah, I'm guessing we are going to do that.
Yeah, that would be really cool, really interesting. Chaim, you have a question? Chaim, you're still muted.
1 second. Yeah, so I have a question about the model so you mentioned that the shallow convection is still on, and I wonder, so I guess you still need a boundary layer scheme, but I wonder why the shallow convection scheme is necessary and if that matters for the precipitation.
So actually, some people started to look at what happens when so shallow convection is necessary. Just I'm not sure it's completely necessary, but it's necessary just the fact that you're still unresolving shallow convection, right? It's just 3.25 kilometer resolution. Shallow convection is the subgrid process when you are considering this type of a grid cell. But there are people who are looking at, they reran the diamond experiment without a shallow convection, and it seems that there are interesting results and maybe better representation, especially if they're considering just, I think they got a better representation for even like tropical cyclones, which I don't think they still fully understand why is that reason, but yes, people are still working on whether or not turning off or turning on the shallow convection. Also, the shallow convection, I think, is a very idealized scheme that we are using. So maybe this is the reason why maybe it's better running the model without it. But yeah, it's part of the process, and they're working on a second version of XShield to run, and maybe they will have an improved version of that in terms of shallow convection.
I have a question. Ilai, so can you tell us what's the range of, like, call it a single deep convection event, and how well it's resolved, especially, and do you think it might, if you improve the resolution, things, the representation will improve as well? And also I wanted to ask about spin up. Is it like, did you spin up the model in like intermediate resolutions, or is there any, like, what was the strategy for spin up, and is it fully spin up?
So I'll start with the last question. The spin up issue is not very large of an issue because it's an atmospheric model only. So you're basically nudging the atmosphere and nudging the mixed layer into a specified SST. So the only thing that you are worried about is just the spin up of the atmosphere, and the spin up of the atmosphere is very fast. So when we're talking about diamond experiment, what the protocol is to disregard the first 10 days of spin up and take only the last 30 days, which is a more or less fine thing to do. The first question about the deep convection. So again, this is the difference between when you're considering, I'm not sure that 3.25 kilometers is the best resolution for resolving deep convection. Again, when we are talking about deep convection, we're talking about things that are 10 to 15 kilometer, laterally and deep, more or less, and waving. So having a 3 kilometer resolution means that we have I don't know, 4 grid boxes to resolve that. Maybe it's not the best one, the best thing, but it's much better than having just 25 kilometers where you don't resolve anything. Of course, that if you're going to a lower resolution, it will be better, but again, the number that I gave computationally for the 7 million CPU hours per simulated year is a huge number, and it was achieved after optimizing the model very highly in GFDL. I heard from another modeling center, I think, I don't remember the number, but the name, but the number that they gave was 3 times the number that XShield is running on, so 21 million CPU hours. So increasing the resolution after that, it's without having a better computational system or a more efficient computational system. It might be okay for a diamond type of simulations where you run for 40 days, but to run for a year or more might not be the greatest
Yeah,
way
the
to go.
blanket always can always pull it to one side at a time, the blanket, of course.
Yeah.
Great, thank you. Any other questions? We encourage questions from students as well. Would like to encourage in the future as well.
Did you also compare the models to observations or only to the simulate models?
So the comparison to observations, one comparison to the observations is this type of thing, but I didn't do most of, if I'm going, so most of the work done to compare to observations are actually done in the, I don't know, this type of thing or this type of thing, which use the diamond simulation. So it's a 40-day run. So you're looking at 1 month and then comparing it to the observations. It's not the greatest way to do that, but it's okay. Another thing that we did is some type of verification of the model, which is available online, where we quantify the biases of XShield compared to observed DIRs. But I don't have them in mind now. Of course, XShield still have biases in a lot of things. They are a bit lower compared to Sim6 models, but again, we're limited in the integration time in that part.
Great. Thank you very much, Ilai. It was really fascinating. Thank you all for coming, and see you all next week.
Thanks.
Thank you.
Thanks, Ilai.
Bye.